So in this video we will discuss the expression for the entropy of an ideal gas. Means we will derive this equation S is equal to 5 by 2 nk plus nk ln and this much. So for that, first of all we should know that according to Boltzmann's entropy relation, entropy S is given by S is equal to K ln omega. Here omega is the thermodynamic probability. Means the number of microstates in a particular macrostate. So let give this as equation 1. So first of all let us calculate this term, that is ln omega. We know that according to Boltzmann's canonical distribution, thermodynamic probability omega is given by n factorial. Let us write in this way: thermodynamic probability omega specified by n1, n2, n3 nk. Here ni is the number of particles in the ith compartment. So number of microstates in a particular macrostates having a system in which there are compartments of unequal size, the value of omega will be n factorial summation I is equal to 1 to k gi to the power ni divided by ni factorial. And remember, if we use this symbol summation of I ni, it means n1 plus n2 plus n3 and so on. But instead, if we use the symbol pi I ni, it means n1 multiplied by n2 multiplied by n3 and so on. So this is the multiplicative summation. Let this is equation 2. Okay. So if we take logarithm of both sides, then we will get ln omega is equal to ln of n factorial summation I 1 to k gi to the power ni divided by ni factorial. So this will be the value, and by simplifying this we will get ln omega is equal to ln n factorial plus summation I, here this is the additive summation, ni ln gi minus ni ln ni plus ni. This quantity. And how we get this term from this term, it is discussed in the I button. Please click on the I button and watch it. Okay. Now ln omega is equal to ln n factorial plus summation I, that is I is equal to 1 to k. We need not write that, only simply we can write as summation I. If we take ni common, then it will be ni ln gi minus ni ln ni plus ni. Okay, sorry, if we take ni common, then here it will be remain 1. Now that is equal to ln n factorial plus summation of I, here ni ln gi by ni plus 1. This is the value of ln n factorial. Okay, let's put this as equation 3. We have already reached the equation 2. Let's put this as equation 3. Now, according to Maxwell's canonical distribution, the value of ni is equal to gi e to the power minus alpha into e to the power minus beta ei. That implies gi by ni, where gi, as we have already discussed, as we have already know, gi is the number of cells in a particular compartment. So gi by ni is equal to, taking this the other, e to the power alpha e to the power beta ei. Okay, so in the topic of Maxwell canonical distribution, we have already calculated that the value of beta is nothing but 1 by kt, where k is the Boltzmann's constant and T is the absolute temperature. Okay, so we can write gi by ni is equal to e to the power alpha e to the power ei by kt. This is equation 4. Now substituting this value in equation 3, we get, substituting this value in equation 3, take substitute at this position, ln gi by ni. So in place of gi by ni, we will substitute this value, then it will be ln omega is equal to, start from this summation of I ni ln, in place of gi by ni we will write e to the power alpha into e to the power ei by kt. Okay, then put it in bracket plus 1 and put here another bracket plus ln n factorial. This is the final value. Now, so here ln e to the power something, so if we take ln e to the power x, then it will be x. So according to this formula, summation of I Ni alpha plus ei by kt plus 1. And if we remove the bracket, then it will make no difference. So let's remove this bracket. Right. Okay. And then plus ln n factorial. Further simplifying this, I ni alpha plus summation of I ni ei by kt plus summation of I ni plus ln n factorial. Now this will be equal to, here alpha is constant for the summation, let take it out of the summation, ni plus, here 1 by kt is constant, let take it out of the summation, I ni ei plus, here summation of ni means that is capital N. So first let us put as it is, summation of ni ln n factorial. Now here this term summation of ni, this means the total number of particles in the system. So here alpha n, because total number of particles is capital N, plus here 1 by kt, and as we have frequently discussed, summation of ni ei, this represents the total energy of the system, that is E total. And then this term also represents the total number of particles, that is capital N plus ln n factorial. And according to kinetic theory of gases, we all know that total energy of a system is given by E total is equal to 3 by 2 nkt. Average energy is given by E average is equal to 3 by 2 kt. This is also from the partition function, we will discuss it later, but the average energy is given by this 3 by 2 kt, and the total energy is we got by multiplying k to the average energy. So alpha n plus 1 by kt into 3 by 2 nkt plus n plus ln n factorial. Here we will cut kt with kt, and 3 by 2 n here plus n, it will be 5 by 2 n plus n into alpha plus ln n factorial. Okay, so which value is this? This is the value of ln omega, and let us put it as equation 5. Okay, also we calculate the value of alpha in Maxwell canonical distribution as alpha is equal to minus log n by v h square by 2 pi mkt to the power 3 by 2. We have already calculated it in Maxwell canonical distribution. So here we will simply put the value of alpha in the equation 5. it is ln omega is equal to 5/2 n plus n into alpha, value of alpha, that is here there is a -1, so write it as -n logarithm of n by v h square by 2 pi mk to the power 3/2 plus ln n factorial. Now if we take the inverse of this term, then this minus symbol will be plus. So let's do that. 5/2 n plus n ln, so by mistakenly I have written here log, this is actually ln, so base should be e, ln v by n, all the term inside the square bracket will be inverse, then only here the minus term will be plus h square by 2 pi mk to the power 3/2 and then ln n factorial. So this is the value of ln omega. So instantly I can go back to the expression for entropy, that is S is equal to K ln omega, and here we have already calculated the value of ln omega. So let's just put the value in this equation. So entropy of an ideal gas is equal to K whole into value of ln omega, that is 5/2 n plus n ln v by n h square by 2 pi mk t. Here we have left the term t by mistakenly, t, right, to the power 3/2, then there is another term left, that is ln n factorial, 5/2 nk plus nk ln v by n h square by 2 pi mkt to the power 3/2 plus k ln n factorial. So this is the required expression, that is the entropy of an ideal gas. Okay.